Good morning. I am Brij Bhushan, and along with Alison Lenhart and Professor David Trumper at the Precision Motion Control Lab at MIT, I'm going to talk about oversampling and averaging and noise analysis for improving control performance. This is a one-slide snapshot of our main results. FPGA enables high-speed input-output and control implementation, with which we are able to reduce the sensing noise by oversampling and averaging. As we can see in the plots here, the noise variance by oversampling and averaging has reduced by 5 times compared to the raw measurements. This low sensing noise enables use of larger gains and hence achieve a larger crossover frequency, 100 Hz with oversampling and averaging versus 50 Hz without oversampling and averaging. In this work, we also make use of spectral tools such as power spectral density and cumulative power spectra plots to identify the various sources of noise and then systematically eliminate or reduce them. The controller was implemented on the FlexLab PCB. The FlexLab PCB is a portable mechatronic system that was developed in a lab for teaching purposes. It is so that students can have a lab experience, hands-on lab experiences even outside a dedicated lab facility. It consists of this bronze T-beam with permanent magnets on each end, which is what we are trying to control. We're trying to control the bend direction and the twist direction of this bronze T-beam. These permanent magnets help in actuation and sensing, actuation using spiral coil traces on the PCB, and in sensing using these Hall effect sensor pairs on each end, which sense the vertical position of the permanent magnets. The PCB also contains onboard power amplifiers for driving the coils, and the controller is implemented on the National Instruments MyRio, which has an inbuilt FPGA. This is the controller architecture. We are measuring the position using Hall sensors of the permanent magnet. That goes to a Hall sensor measuring circuit, which implements an anti-aliasing filter at 20 kHz. This then is sampled in the NI MyRio FPGA at 250 kHz sample rate. Then a 256-point moving average filter is implemented, which then the data is stored, and then the control loop reads the data at 100 kHz loop rate, which then is also output through the DAC at the same rate. We have a push-pull linear power amplifier on the PCB, which drives the PCB coils and hence actuating the magnets, closing the loop. The data is then also buffered to the real-time interface loop, where the UI elements and the dynamic signal analyzer to measure the Bode plots have been implemented. Further, data is also buffered to the host PC, where more complex analysis such as the spectral analysis takes place. So what do we mean by oversampling and averaging? There are two main sources of noise in sampled signals, the sensor noise and the analog to digital converter or the ADC noise. So this is a plot between the power spectral density versus frequency. The area under the power spectral density curve gives us the total noise variance at a given bandwidth or from 0 till that frequency. If you look at the ADC noise can be assumed to have a flat noise spectra till the Nyquist frequency. The total noise variance of the ADC is constant, which means that if I increase the sampling frequency, the power spectral density comes down till the new Nyquist, such that the area under the power spectral density curve or the noise variance is constant. The other source of noise, the sensor noise, can have any spectra. It need not be Gaussian, but we usually assume that beyond the anti-aliasing filter frequency, the sensor noise rolls off. So it has a spectra, it has spectral bandwidth, usually till the anti-aliasing filter frequency. So what we do in oversampling and averaging is that we try to sample as fast as we can to reduce the power spectral density of the ADC noise. Then we implement a low-pass filter till frequency FLPF, which is sufficiently above my crossover frequency. The resulting total noise power or the noise variance is the area under the curve for both the sensor noise and the ADC noise till the frequency of the low pass filter. And hence, a lot of all the noise elements beyond the low pass filter frequency are eliminated. As we can see from the plot here, the major benefit that we get is that the ADC noise is significantly reduced, Further, some of the sensor noise till the anti-aliasing filter frequency is also reduced. We first test the impact of oversampling and averaging on a grounded ADC input. Plot on the left is a raw ADC input, and plot on the right is after oversampling and averaging with a 256-point moving average filter. What we find is that oversampling and averaging reduces noise considerably, and the resultant behavior is that the 12-bit ADC is behaving almost like a 16-bit ADC till 1 kilohertz bandwidth. Since most of our crossover frequencies are in the 100 hertz range, this is sufficient, and we proceed further with implementation of the controller. An important consideration in implementation of oversampling and averaging is the associated phase drop due to the low-pass filter as well as the zero-order hold implementation. We implement a 256-point moving average filter at 250 kilohertz as a low-pass filter, and it's a linear phase FIR filter, and we get a corresponding phase drop of 18 degrees at 100 hertz. On the other hand, we get negligible phase drop due to implementing a controller at 100 kilohertz on the FPGA. If you would have implemented a controller directly on the real-time processor, we are limited to a maximum loop rate of 2 kilohertz, and the corresponding phase drop at 100 hertz crossover frequency would have been around 9 degrees. Therefore, with oversampling and averaging, by losing 9 additional degrees of phase, we are able to make the ADC behave from a 12-bit ADC behave as if it's a 16-bit ADC. And this helps us drastically to reduce the sensing noise, and therefore helps us achieve higher control performance. We measure the planned Bode plots in bend and twist directions. An interesting thing to note is that we are able to measure these high frequency dynamics because of our improved sensing resolution by oversampling and averaging. Otherwise, the amplitudes at these high frequencies are small, and they would just merge into the ADC quantization noise. We decouple our measurements in the bend direction as well as the twist direction of the T-beam. This decoupling helps make the resonances at the first two modes, 11 Hz and 32 Hz, independent in each direction. The high frequency modes limit the achievable crossover frequency in bend and twist directions. In the bend direction, this is due to the resonance at 336 Hz, which corresponds to the fifth mode shape. In the twist direction, it is due to the resonance at 154 Hz, which corresponds to the third mode shape. What is interesting to note here is that the third mode shape corresponds to the beam moving up and down at the middle. So we would expect to have a corresponding 0 in the bend direction, and that this mode should not have been observable in the twist direction. If you look at the bend direction, we do see a corresponding 0 at that frequency. In the twist direction, this mode becomes visible because of tolerances in assembly of the permanent magnets, which are not perfectly symmetric, as well as asymmetry in the manufacturing of the bronze beam. And hence, this mode gets parasitically coupled in the twist direction. That makes this mode observable but uncontrollable, and therefore places strong limits at this frequency. One thing to note is that because this is a parasitically coupled mode, the amplitudes are relatively small of the resonance. For our controller, we implement standard PID controllers in both bend and twist directions, achieving a crossover frequency of 100 Hz with 40 degrees of phase margin in both directions. In addition, we also implement a notch filter in the bend direction at 336 Hz to reduce the impact of that resonance. In the twist direction, we do not implement notch filters because this frequency, the 154 Hz frequency, is very close to our desired crossover frequency of 100 Hz. And instead, even though there are multiple crossovers, we ensure stability by keeping the phase above negative 180 degrees at all those points. These are the corresponding step responses in both bend and twist directions. The measured step responses match the model step responses reasonably well. An interesting thing to note here is that the jerk in the bend direction due to the step excites the third harmonic at 154 Hz, which is parasitically visible in the twist direction as these oscillations. Now, these oscillations are visible because of our improved sensor resolution due to oversampling and averaging. In the raw signal, these oscillations do exist, but they get merged into the quantization noise, and hence the dynamics are not discernible. These are the sensing noise performance results in closed loop. With oversampling and averaging, we're able to reduce the sensing noise standard deviation to almost 16 microvolts in both bend and twist direction. This corresponds to 50 nanometer positioning noise in the bend direction and 3.3 microradian positioning noise in the twist direction. The corresponding power spectral density and the cumulative power spectra plots show where the maximum noise injection is. In the bend direction, the noise injection is at 45 Hertz, which we believe is due to external sources. Whereas in the twist direction, as expected, we have a high noise injection due to the parasitic mode at 154 Hertz. To summarize, FPGA allows high-speed input-output and controller implementation. Utilizing this high-speed sampling, along with oversampling and averaging, we're able to reduce the sensing noise significantly. Reduced sensing noise allows us to achieve higher controller performance by being able to use larger gains and achieving higher crossover frequency. In addition, oversampling and averaging makes implementation of anti-aliasing filters easier because now the anti-aliasing filter can only have a gradual slope because of the much higher sampling Nyquist frequency. The FlexLab PCB design files as well as the LabVIEW code used in this work are open source and are available to be downloaded and used freely from these links. We're happy to take any questions in the question answer session, and if there is interest, we can also show a live demo of the system in action. Thank you.